Hello, I am Seema and welcome to part 29 of the chapter Hydrocarbons. We were doing the chemical properties of alkenes. So we'll move ahead with the same discussion. In this video, I'm going to talk of the last two properties of alkenes, that is ozonolysis and polymerization. So let us start with the first one, that is ozonolysis. Do you remember that we have studied about electrolysis? I'm just talking of the similarity in the terms ozonolysis and electrolysis. You know that lysis means breaking down. And why did we use the term electrolysis? Where we were using electricity to cause the breaking down of a salt into its ions, right? Or for the breaking down of a molecule. Not actually a molecule if it is ionic in nature. But we use electricity to break down the ionic compound. So, using the same terminology and our understanding, lysis we understand means breaking down of a molecule. Ozono means, there we said electrolysis. It means electricity is causing the lysis or the breaking down. So, ozonolysis would mean that ozone is causing the breaking down, right? So, ozonolysis of alkenes. Ozone is causing the breaking down of what? Of alkene. Now, what is there in an alkene which is so special that ozone will come and break it down? Out of all the hydrocarbons, how do we identify alkenes? Alkenes are those molecules in which, or those hydrocarbons in which between two carbon atoms there is a double bond, at least one double bond. That makes it an alkene. So, it means that ozone will come and break the alkene at that point, which is making it an alkene. So, it will come and break the molecule wherever the double bond exists. So, when it breaks down the molecule breaks and forms smaller molecules, and it will give you two products. And both the products, what the products will be, will depend on what is attached to the two carbons which have been, which were connected by a double bond. So, whatever is attached to that, that will decide the product. So, let us now come to the ozonolysis. One important thing to remember is that since ozone is going to target the double bond of the alkene and the two products are going to depend on the two carbons which were combined by a double bond, this becomes a tool to identify which are the two carbon atoms which have the double bond. We can't see molecules in reality. So you just know it's an alkene, but which alkene is it? That you could identify. This could be used as a test to find out where exactly is the double bond in the chain. You'll understand this as we do ozonolysis. So you have an alkene, that is propene. When propene is made to react with ozone, and this reaction takes place at minus 78 degrees Celsius. It takes place at a very low temperature. At this temperature, the ozonolysis takes place and it results in the formation of an intermediate which is known as the ozonide. It's very important to remember here that when ozonolysis takes place, it takes place in two steps. The first step is the formation of an intermediate known as the ozonide. In the second step, the ozonide is made to react with zinc and water. This is what is in your syllabus. It is made to react with zinc and water and it causes the ozonolysis and it gives you the two products. So this blue part is what is not there in your syllabus, but I'll be throwing in this little additional information for your future reference. So you have propene. Propene reacts with ozone at a very low temperature, results in the formation of propene ozonide. So how is the ozonide formed? The place wherever the double bond is between the two carbon atoms, if you are, let us say you just given a reaction and you're told that carry out the ozonolysis of this, what will you do? You will target the two carbons where the where the double bond is, remove the double bond and insert the ozone, that is all the three oxygen atoms in this way. So the two carbons, the two bonds break, the carbons make one bond each with oxygen on top, one bond each with two oxygens here, and these two oxygens form their bond. This structure is known as the ozonide. Since it was made from propene, it is known as propene ozonide. Now, in the first step, the ozonide or the intermediate was formed. In the second step, what happens? You make it react with zinc and water. And when you make it react, or in the presence of zinc and water, what happens? The ozonide, it breaks. It breaks into two products. The ozonide molecule, it breaks in this way. This oxygen in the center is left out, and the two oxygens which are attached to the two carbons, they are present. So when this molecule, it breaks, it results in the formation of these two products. What the two products will be? Look at the two carbons, what do they have? They have this carbon is attached to oxygens, of course, but it is or it had the double bond initially, but it is attached to a hydrogen and a methyl group, which means one alkyl group and one hydrogen. So what will happen is that the hydrogen and the alkyl group remain where they are, and this, as this breaks, this carbon forms a double bond with this oxygen. When it forms a double bond with this oxygen, what do you have? You have CH3, CHO, and CH3, CH double bond O. CHO is what functional group? It is an aldehyde, right? So you get ethanol. And this is ethanol, and on this side you had carbon with two hydrogens, so the two hydrogens remain as such. This carbon forms a double bond with this oxygen. So what is the product that you get? You get HCHO. And what is HCHO? It is methanol. So you get methanol and ethanol are the two products that you obtain on ozonolysis of propene. Now the product would vary if instead of this hydrogen you had an alkyl group here. Then let us say this, instead of this hydrogen was also a methyl group. So you had CH3, C, CH3. So CH3, CO, CH3. Then what would it be? It would be a ketone, right? R, CO, R would be a ketone. So that is how you get the products, and that is how you guess what the product would be. You're not going to change anything on the side of the two carbons. Whatever they are attached to, they are attached to. The only change that occurs in the end is that the carbon forms a double bond with oxygen. The carbon, or you could say for the final result, if you just break this bond, this will form two products. One will be CH2 double bond O, the other on this side will be CH3CH double bond O. Those would be your products. So look at this other example. You have 2-methyl propene. 2-methyl propene now has two methyl groups attached to this carbon, and there's a double bond and there are two hydrogens attached. So you can guess now what will happen when ozonolysis occurs. When ozonolysis occurs, an ozonide will be formed in the first step. So you can break the bond, attach it to oxygen, one oxygen here, two oxygens here, both the oxygens attached to each other, results in the formation of an ozonide. Then the ozonide breaks, or it cleaves, and it results in the formation of the two products that we are expecting. And what are the two products that you would get? You would get, again with zinc and water, the two products that you get, the two methyls, the carbons remains as such. This carbon forms a double bond with this oxygen, and this carbon forms a double bond with this oxygen. All other bonds are broken, so you get two products, CH3, C double bond O, CH3, and here you get HCHO. That is, you get methanol here, but since both of them were substituted, you get propane 2O, right? So this was ozonolysis. Now the little additional information that I wanted to throw in. This second step that you see with zinc and water, this actually is reductive quenching. You're carrying out the quenching of the intermediate, that is the ozonide that is formed. Quenching can be reductive, it can be oxidative too. Reductive quenching is done with zinc and water. It can also be done with phosphine. It can also be done with dimethyl sulfide. And oxidative quenching can be done with hydrogen peroxide. In your syllabus, we only do the quenching, that is reductive quenching with zinc and water, and we do not even mention these terms because this is something that you will be studying in higher classes. So, reductive quenching can also take place, but in reductive quenching, these are the products that you would get. In oxidative quenching, when you carry out the oxidative quenching with hydrogen peroxide, the products would be, how would you determine the products? If you have if you have a situation like this, where two methyl groups are attached to a carbon, then of course the product will be a ketone. If you have one carbon and one hydrogen, the product, since it is oxidative quenching, quenching is occurring, but an oxygen is also adding to it. In that case, you will get a carboxylic acid. And if they were both hydrogens, then of course you would get aldehyde. So that is the only difference between the products of oxidative quenching and reductive quenching. But even if you do not get them right now, it is not important. I just wanted to throw in an idea that such a thing exists, and in higher classes when you study about it, when you do the mechanism, you will understand this better. Right now, it is sufficient for you to know that when ozonolysis occurs, you get two products. The first step involves the formation of an ozonide, and in the second step, in the presence of zinc and water, the two products are formed. And you do not change anything in the two carbons. Whatever they are attached to, the other two bonds remain as such, and you just add a double bond or wherever the double bond broke. And that will give you your products. And then name them, give the IUPAC names for those products. So that was ozonolysis of alkenes. There are a few questions on ozonolysis in the textbook exercise, and I would like to cover that. And since I wanted to finish this topic first, I will be doing those problems in part 30. So we'll do some NCERT exercise questions based on ozonolysis in the next video. And before coming to the conclusion, let us now talk of the last property, that is polymerization. You know, little alkene molecules, they have double bonds. What happens if a double bond breaks? Whenever there's a double bond, let us say, how do I make it here? Okay. So there's a CH2 double bond CH2. This is an alkene molecule. A CH2 double bond CH2. CH2 double bond CH2. CH2 double bond CH2. What have I done? I've written down 4 molecules of ethene. Theoretically, if I just remove one bond from each of these, removing one bond would mean, it's easier to use my finger. Okay. Removing one bond would mean that each carbon has got back its electron. You agree with me? Breaking a bond is, what is a bond? A bond is a shared pair of electrons. So when you break a bond, both the carbons, this is our friendship, we'll share, we are holding hands. And if we break our friendship, we take back our hands. Your hand goes back to you, my hand comes back to me. So both the carbons, they take back their electrons, that means the bond is broken. So if the bond is broken, every carbon now has that one dangling electron and the octet is not complete. So what do these molecules do? This remains dangling as it is. These two, they decide to form a bond, single bond between them. These two will form a single bond. They'll share the pair of electrons and form single bonds. And you know that single bonds are stronger than double bonds. Therefore, this larger giant molecule as it is formed, this will be far more stable in comparison to an alkene, which is so reactive because of the presence of that weaker pi bond. And I could make only 4 of these. Imagine this, that it's in a bracket and this multiplies n times. You get a giant molecule of millions of ethene molecules which have been attached to each other, forming a giant molecule. Now, the single ethene molecule was a single one, so we call it a monomer. But when it forms, it joins to so many other ethene molecules, the giant molecule is known as a polymer. There are polyethene molecules. Poly means many. Mono means one. So when you have alkenes which can combine like this to form giant molecules, the process is known as polymerization. And polymerization results in a saturated compound which is far more stable. And that is the reason, you know, when I said the word polythene, you use those polythene bags, and we know it is of such great environment concern that you have these polythene bags and they are not non-biodegradable, and they are not going to go from the earth for many years, and therefore we are polluting the environment with all the polythene that is created. But the molecule that is created, that is the polythene or any alkene or as a result of polymerization, the plastics that are formed, they are very sturdy, they are very stable, they are chemically inert, therefore they are actually very useful. The problem is not about the molecules, the problem is more about the management of how these molecules have not been managed properly. Their recycling was not focused on initially, which led to so much of pollution on Earth. All these Pepsi bottles and water bottles that we get in the market, all of that is the result. All those plastics are the result of the buckets and mugs and so many your TV cabinets. There's so much of plastic that we use. All of that is the result of the reaction known as polymerization. So let's just briefly read about it. Polyethylene or polythene, as we miss the E in the middle just to make it easier to, because polythene, in a way, Y and E, they sound the same, so we just say polythene. But polyethylene, this molecule is obtained by the combination of a large number of ethene molecules and at a high temperature and pressure. When you increase the temperature and pressure, the monomers, they start polymerizing. The second bond, which is a weaker bond, with that much of heat, it breaks and results in the formation of single bonds on the sides. So you get at high temperature and pressure, due to the pressure, the molecules come close and the dangling electrons on each of the carbons, they start joining with each other, resulting in the formation of single bonds. So, and this reaction takes place in the presence of a catalyst. The single units are known as monomers, and monomers on polymerization give the resultant polymer. What you get is the polymer, and what you started with was the monomer, and this process is known as polymerization. So, for example, N molecules of ethene are taken at high temperature and pressure in the presence of a catalyst. And how do we represent a polythene molecule? You put a bracket, you show the dangling bond. The dangling bond says that this is a single bond and it is extending, the single electron which is going out. Then we put a bracket and we put N. All of them have joined together to form this giant molecule, which is polythene. So this is how we'll represent it. We cannot make a million molecules of ethene and then show it. So this is an easier way, that whatever is the number N, you have those many ethene molecules combined together to form the polythene. Similarly, if you have propene, propene would also be polymerized in the same way. In the case of propene, you see these are the two carbons which will get the dangling electrons, because the pi bond will break here, so this carbon and this carbon. So the polymerization would still take place in the same way, only now for every carbon there is one hydrogen and one methyl group. So let us say the first one is a hydrogen and a methyl group. So I'll put a hydrogen here and the methyl group will come here. For the second molecule, there's only one hydrogen and there's a methyl group. For the third molecule, there's one hydrogen, there's a methyl group attached to the carbon, there's a methyl group attached to this carbon. So this now becomes polypropene, right? So this is the second polymer that you get, that is polypropene. So what is the process? The same process. Propene was taken at high temperature and pressure in the presence of a catalyst. It gives us polypropene. How do we represent it? We write carbon. The two carbons which have the double bond and the dangling electrons are written on the two sides of the bracket. Everything else which is attached to the two carbons with the double bonds is written above and below. There will be only two other things that it will be attached to, because carbon is tetravalent. One bond on this side, one bond on this side, so there can be only two other bonds. So even if there were two other methyl groups, you would have attached one methyl here and one methyl here, which actually we just write the H here. It means the same thing, that the hydrogen is on top here. So the two carbons with the double bond are put inside the bracket, and of course the rest of the species are also put around the carbons, but you show the dangling electrons, so that you show that the polymerization has taken place due to these two carbon atoms combining with the molecules, the similar carbon atoms of the other molecules. So where do we have these, where do we use these polymerized molecules or plastics? Milk crates are made out of these, plastic buckets are made out of these. So polypropene, you have milk crates and plastic buckets, it's stronger. And polymers like polythene, you make plastic bags, you make those squeezy bottles, the refrigerator dishes, toys, pipes, radio, TV cabinets, etc. Everything. We use plastics abundantly, a lot in our everyday life. But the problem is that this excessive use of polymers has become an environmental concern. And I already spoke about it a little bit, that if we learned polythenes are not bad. We are not supposed to hate polythenes. They are very useful. They are sturdy. They can be recycled. They can be used again and again. It's a very good, it's a very good product to use. Only it has to be used and disposed of wisely. If we learn to do that, we have, ever since we discovered plastics or we invented them, life has become much easier. They are cheaper, they are sturdier, they are colorful. So they have added a lot to the quality of life. So you cannot imagine life without plastics, but we have to imagine how to not harm our environment even if we are using them. So these were the chemical properties of alkenes. In the next video, I'll be doing the few numerical problems that are based on ozonolysis of alkenes. So with this, I'll wind up today's video. If you wish to watch the other videos in this chapter, the link to the chapter, the playlist of the chapter will appear on your video. Click that and watch all the videos on this chapter. On my channel, you can go to the layout of the entire, below the first 3-4 videos, that the latest ones that I upload, you can just go down to find different portions for different classes, for 11th, for 12th, for 9th and 10th. You can go and click the various playlists of different chapters and find the entire chapters there. I haven't completed all of them yet, and I am still doing them, but whatever content is there in the library, you are welcome to watch it and benefit from it. So with this, I'll finish the video. Thank you for watching, and subscribe to my channel, recommend it to your friends, and please keep returning for more videos in chemistry. Bye-bye for now.